In this segment, we go through another random incidence example, one that does not involve a Poisson process, but a much simpler arrival process. We do this for two reasons. One is because of the simplicity of the example, perhaps the intuition will be a little more transparent. And the second reason is to illustrate that we're dealing with a phenomenon that's not specific to the Poisson process, but is much more general. The example is as follows. We have an arrival process in which arrivals happen at random, and the consecutive inter-arrival times are independent, identically distributed random variables. However, unlike the Poisson process, these inter-arrival times are not exponential random variables, but instead we assume that they're either 5 or 10 minutes with equal probability. So we have an arrival, the next arrival may happen 5 minutes later, the next arrival may again happen 5 minutes later, then maybe we get an inter-arrival interval of length 10, then maybe another inter-arrival interval of length 10, followed by one of 5, and so on. What is the expected value of the kth inter-arrival time? Well, an inter-arrival time is with probability 1/2 of length 5 and with probability 1/2 of length 10. So the average inter-arrival time is 7.5. Now you show up at a random time. And by random we mean a time that's completely uncoordinated with the arrival process. You show up at some point in time and you look at the inter-arrival interval in which you fall, and you're interested in the length of that particular inter-arrival interval. What is the probability that you fall inside a 5-minute inter-arrival interval? Since intervals of length 5 are as likely as intervals of length 10, in the long run there's going to be roughly as many 5-minute intervals as there will be 10-minute intervals. On the other hand, the 10-minute intervals occupy twice as much space on the real line. And for this reason, it is 2 times more likely that you will fall in a 10-minute interval rather than a 5-minute interval. In other words, the probability of falling in a 5-minute interval is going to be 1/3, whereas the probability of falling in a 10-minute interval is going to be 2/3. For this reason, the expected length of the inter-arrival interval that you get to see when you arrive is equal to, with probability 1/3 you see a 5, and with probability 2/3 you see a 10, and this number evaluates approximately to 8.3, which is indeed larger than 7.5. The conclusion from this example is similar to the one that we had for the Poisson process. Although the average inter-arrival time is 7.5, when you show up at a random time, you're more likely to fall in a larger interval, and for that reason, on the average, you will be seeing longer inter-arrival intervals. The calculations that we carried through in that simple example can be generalized for more general arrival processes called renewal processes. In a renewal process, once more, the consecutive inter-arrival times are independent, identically distributed random variables, but they have a general distribution. For this case, there's a formula again that tells us the length or the expected length of the inter-arrival interval that you get to see. But the main message from this example is that it does make a difference how you sample, how you choose what to watch and what to measure. It makes a difference whether you decide to measure the kth inter-arrival time and its average value, or to decide to measure an inter-arrival time that's chosen by showing up at a random time. The two methods of sampling give you different results, and we will see next a few examples that have this particular flavor.